We're happy to have Daniel Baumann here from Cambridge. Daniel did his undergrad at Cambridge before moving to Princeton. He did his PhD with Paul Steinhardt. And then he, after stints in Harvard and the IS, he joined the faculty at Cambridge a few years ago. And so today he's going to tell us about probing the nature of inflation.
Okay. Yeah, thanks a lot, Dan. Yeah, thanks everybody for coming. So what I wanted to do today is tell you a little bit what Dan and I have been thinking about in the last year or so. And I should warn you from the beginning, these are kind of slides put together from several talks for several audiences and so on. So please stop me at any time if I'm assuming something that you don't know, or we can keep this a little bit informal maybe. All right. Okay, so just to remind you the status of observations. This is what we know today, thanks largely to observations made by Planck. So we know that primordial density perturbations span superhorizon scales at recombination. They're very nearly scale invariant, Gaussian, and adiabatic. Yeah? So there are no relative fluctuations between different fluid components, at least at the level of precision that we're probing these fluctuations. And then, of course, as you also have heard, I'm sure, there's a debate going on right now whether primordial tensor fluctuations have been detected in addition to these scalar density fluctuations, or whether we're just seeing dust. So I want to entertain both of these possibilities and describe to you what it would imply for the physics of inflation if we take these observations and maybe together combined with this one at face value. Okay, so this can also be summarized by three key numbers that I hope most of you have seen before. So the scalar spectral index parameterizes the deviation from scale invariance. So we have observed, in fact, that the fluctuations aren't precisely scale invariant, but the deviation is only at the percent level. Okay. We have also observed that this FNL parameter, which parameterizes the size of interactions in these higher order correlations in the fluctuations, is small, less than of order 100. This number is slightly dependent on this type of shape of these fluctuations that you're assuming. And then finally, this parameter R, which is the amount of tensor fluctuations. And I'm going to discuss what implication a value of R bigger than 1% would have. Okay? And just for reference, what Bicep was claiming to observe was a value of R of 0.2. Yeah? So an order of magnitude bigger than this threshold value that I'm going to consider in this talk. And so what I want to discuss is what these three numbers roughly imply about the nature of inflation. If we put these things together, what do we learn? Okay? So the way you have usually seen this discussed, I'm sure, is people propose to you that there was a fundamental scalar field in the early universe that had a potential shape that was given by some higher power. And then that potential shape was driving inflation, and you analyze fluctuations on top of this classical evolution of the field. Okay? And so what I want to highlight is that this choice of a single slowly rolling scalar field is really a choice made by convenience. Okay? Or here I'm describing it as a lamppost effect, where one of the reasons we're studying this is just because it's simple and it's computable. Okay? Of course, that's different from nature choosing a physical mechanism, and so we should explore what kind of deviations we can expect or probe away from the scenarios that we have the easiest time computing on our desks. Yeah? But then there's a question, is this kind of simple picture that we have introduced, is that favored by data? Okay? And of course, as you know, at the moment, it is favored by data. There's no single observation that speaks against taking the simple ansatz of a single slowly rolling scalar field. But the reason to study deviations, I think, away from single slowly rolling scalar fields is in order to quantify how much confidence we have in that single picture, to have parameters, quantifiable deviations away from that we can bound, where you could put constraints on parameters and know, with what level of quantitative significance we should believe in this kind of picture. All right? So just to highlight, there's several ways in which you could imagine, not living in this preferred place in parameter space. You could imagine that the dynamics isn't slow roll, some deviation from this simple dynamical picture. So this is what I'm indicating by this axis here. You could imagine that it's not just a single field that is driving the expansion, but there are multiple fields relevant for this, and fluctuations in these multiple fields. Okay? And I want to show you examples for both of these classes of of extensions to single field slow roll, and tell you how much the data tells us about these two corners of these two axes in the parameter space of theories. Okay. It's also very natural to expect that you have deviations from the simple picture, just if you think about it from a more fundamental perspective. That I think hardly anybody believes that a single scalar field coupled to gravity is all there is in the early universe. And in fact, especially because we know that gravity itself is not a complete theory up to arbitrarily high energies, there need to be new degrees of freedom, at least when we hit the Planck scale, and more likely at scales below the Planck scale. So it's a rather strong assumption to say that this new degree of freedom that we're postulating in the early universe isn't coupled at all to these new degrees of freedom that we know have to appear at some point. And what's special about inflation, in fact, is that this inflaton field here is sensitive to these couplings. So assuming them away is making a strong assumption about this dynamics. And if we parameterize our ignorance in a more general way, we will in general see rather large effects from these type of couplings. Okay? So we'd like to see what the data has to say about the different classes of interactions that we can introduce at this level. And so this goes under the name of effective field theories. Okay? Most of you have, I'm sure, used effective field theories, even if you didn't call them that way. Okay? So whenever you coarse grain over some detailed microscopic dynamics of a system, you're effectively doing effective field theory. You're just looking at the long wavelength behavior of the system, and which doesn't mean you're ignoring the microscopic details, but it means that you're parameterizing the microscopic details in terms of just a few fundamental constants, parameters of your long wavelength theory here. So a classic example is fluids. Yeah? Of course, the fluid is made out of atoms and molecules, and these atoms and molecules will determine the fluid properties, the long wavelength properties of the fluid, like viscosity, sound speed, and so on. So often it's such an obvious concept that you just do it without even giving it a name. Okay? In particle physics, you do the same. You typically don't know the theory up to arbitrary high energies. You don't know what the degrees of freedom living at close to the Planck scale are. But you can parameterize the ignorance and postulate a set of fields at low energies. Those are the set of fields that you want to keep track of. So this might be the inflaton, or it might be an extra field that's also light during inflation. And then you simply write down the most general set of interactions that these light degrees of freedom can have. Okay? And that's, I would claim, is kind of making the minimal set of assumptions about what the fundamental nature of the theory is. Okay? So I want to look today at two particular classes of these effects from integrating out these short modes. So the first class of term that I want to look at is a higher derivative correction to the kinetic term of the inflaton field. So typically, slow roll inflation is described by Lagrangian like this. Here I'm just looking at the next higher order corrections to the kinetic term. Okay? And as you can easily see, if I expand this action in terms of a background field, homogeneous background field in small fluctuations, then those small fluctuations will have the property that they have a spontaneously broken Lorentz invariance, and they will propagate with a non-trivial sound speed in general. Okay? Which means that time derivative and spatial derivatives aren't treated on unequal footings. Momentum and energy aren't treated on the same footing. And that's of course possible because the background expansion is breaking, is time dependent, and so nothing guarantees for you that the fluctuations are propagating at the speed of light. Okay? So that's one important coupling that you can have that induces at the level of the fluctuations that we observe a sound speed and the fluctuations. Okay? And so this sound speed is going to be the key parameter that I'm going to be discussing. And then the second class of deformations of slow roll inflation that I want to discuss is couplings to extra light fields. And I'm going to look at a special class of couplings, which are also corrections to the kinetic term. So it's effectively like a field space metric that I'm adding to the inflaton dynamics. And the reason it's nice to focus on these derivative interactions is that they don't break the underlying shift symmetry or the flatness of this potential. So scale invariance, which I told you was the number one observable that we have that the data is giving to us, will be guaranteed for these type of theories. Although they're higher order interactions, they respect a shift symmetry for the inflaton field. And so the fluctuations will still, even with this non-trivial dynamics or non-trivial couplings, ultimately the fluctuations will be scale invariant. Okay? Okay, so this is going to be the outline of the rest of the talk. I want to study these two classes of deformations away from slow roll. First, inflation with a small sound speed. And then, depending on how much time I have, I will tell you a little bit about couplings to extra light fields. Okay? And as I said, please do stop me at any time. Yeah?
So presumably you've got a whole class, slew of operators, and so you just picked those two in particular?
Those, in fact, are the lowest dimension operators, given the rules that I was telling you.
You the one lambda before is
Yeah, if you look at this one, this is the lowest dimension operator I can make, just that respects the shift symmetry of the inflaton field, and isn't a coupling to additional degrees of freedom. Just because I have to match up the Lorentz indices, then so it has to be that guy. And again, and this is the lowest dimension operator that I'm allowed to have, if I do have, in addition to the inflaton field, a second degree of freedom. So yeah, and later we're going to see that actually this way of writing the effective action isn't quite sufficient, but we're going to get to that. But at this point, you should be thinking that, yeah, what I mean here by ... is an infinite series of all of these interactions, but there's an expansion in the ratios of energy over the scale here. And so I'm always assuming that the scale here is above the Hubble scale. When we're making measurements in the CMB, we're always measuring things when they're frozen during inflation, so at frequencies of order the Hubble scale. So these effects are suppressed by ratios of Hubble to the cutoff scale lambda. Okay, so let me start first with this dimension 8 operator.
What about complications in the propagation of the waves inside the horizon? I mean, you've got k to the fourth type terms. Does that give you issues with trying to deal with a really high frequency spatial oscillation?
Well, actually, in fact, what happens, because when I was writing this, I'm writing this for the background fields. Yeah? So here I try to indicate what happens if I split this field into a time-dependent homogeneous field and a fluctuation. Then actually this dimension 8 operator will have contributions at quadratic order. Yeah? And those quadratic fluctuations propagate with a sound speed and so on. So there are constraints on the sound speed that they have to, sound speed has to be positive and things like that for these fluctuations here to be stable.
So you don't have to worry about things like nonlinearities, k prime, the couplings at very high k relative to Aj.
Well, I don't.
Before you cross the horizon, it frees out.
Yeah, I don't. So the thing is, you should also. This is also. I mean, I shouldn't be. It's true that in this theory here breaks down at frequencies of order lambda. That's a general feature of any effective theory, and at that frequency, I have to integrate in new degrees of extra the background field. Yeah. So we're going to see this actually in much more detail a little bit later.
Okay.
But
I'll leave that.
yeah. But it's true. It's true that as written here, especially when I truncated it like this theory isn't valid to arbitrary high frequencies. There's this cutoff scale at which the theory breaks down. Yeah. And what all this is telling you is that at that scale, the theory as written here is incomplete. In fact, here we see it. Yeah. If I go to higher frequencies, I stop. These basically these degrees of freedom have to be taken into account. Yeah. So that can happen in effective theories, that it can look as if, but it happens precisely at the scale that you expect it to happen. So, if you have some higher dimension operator suppressed by a scale, you expect that theory at that scale of the cutoff to predict negative probabilities and things like that.
I'm thinking of HA actually propagates, and the relevant thing is not K physical, but K covariant. I mean, getting into Bunch-Davies vacuum, for example,
sure.
Be an issue once you start to do all of these corrections.
Yeah, maybe we can talk about it. I think deep inside of the horizon, there's not so much difference between the physical and the co-moving scale because we are approximating flat space, and so. And there is a story of how you define Bunch-Davies even without taking the limit to arbitrary high frequencies, just as the adiabatic vacuum at any given finite momentum. But yeah. Okay, what I want to show you first, though, is that so we have this important parameter, which is the sound speed of the fluctuations. That parameter is precise. This single type of deformation that I'm discussing is encapsulated by one parameter. And I want to show you that there's a special value for this sound speed at which there's a qualitative transition between two regimes. So a theoretical threshold where we really would be learning something if we were to discover that the sound speed is to the left or to the right of that particular value. And so I want to spend some time showing you what that value is, and then show you how observations tell us where we live in this parameter space at the moment. And in particular, kind of the question we're trying to decide is whether, very broadly, roughly, whether inflation was driven by perturbative physics, where I can really, honestly imagine that there is an expansion like this. The speed of the inflaton field is small relative to the scale of this new physics. Okay? And this is just a perturbative correction to slow roll dynamics. And then you can show that the speed of sound is actually close to 1 if you can treat this higher order interaction as perturbative. The opposite extreme is where actually I should really be taking seriously this infinite series of terms. The whole dynamics here is not described well by just this perturbative truncation. And this happens when the speed of the inflaton field is in fact of order, this cutoff scale lambda. And then you can see that this is unsuppressed. This interaction here is order 1, and any higher order term would be of the same order and shouldn't have been ignored. Okay? And that would correspond to the regime where the sound speed is much smaller than 1. But I want to show you now there's a sharp criteria that divides these two regimes, a very specific value for the sound speed, rather than these twiddles and asymptotic limits that I've shown you here. So this is very similar to what people did at the LHC, where they tried to decide whether electric symmetry breaking was driven by perturbative physics like the Higgs mechanism or non-perturbative physics like Technicolor. And there, of course, it has been decided in favor of the Higgs mechanism. And so something very similar we'd like to decide for inflation as well, whether it's a perturbative expansion or whether there's some non-perturbative physics that we have to understand.
It would really help if you wrote the formula for CS.
Sorry?
It would really help if you wrote the formula for CS.
The formula for...
Speed of sound?
Yes.
I can't expand in my head.
You mean here?
Yeah.
Yeah, I can show you. So if...
Sorry, it's not even
That's fine, yeah. Okay, so we have an interaction like this. We expand this field in terms of some background phi bar of t plus delta phi. Okay, and so if I then look, for example, at there will be a cross term phi bar dot delta phi dot, yeah, squared divided by lambda to the fourth, yeah, but no such cross terms for spatial derivatives, okay, which means that now because of this cross term now, yeah, okay.
So the difference of the speed of sound from 1 is phi dot squared over minus squared.
Yes, yes, okay.
Sorry.
No, it's fine. That's fine. Okay. So since we want to describe this transition between these two regimes, we actually need a description of the physics that's more general than this effective action for the background field, because precisely this regime of non-perturbative physics is precisely where this effective action for the background field is breaking down. Okay. So let me just very quickly introduce a framework in which you can in fact describe in a unified way the entire range of CS from very small values to 1. And that's a framework that focuses directly on the fluctuations. So rather than writing down an effective action for the background field and then expanding it in terms of, or for the total inflaton field and expanding it in terms of background and fluctuations, it focuses directly on the fluctuations. So imagine you had some space-time, and that space-time is filled with some matter fields. And then you give some of the matter fields time-dependent expectation values. Okay? Those time-dependent expectations values will introduce a preferred time slicing in the space-time. Okay? This might be a fundamental scalar field. This might be the energy density of a fluid. This might be anything. It might be a solid. Yeah? So the only thing that's going to be important for us is that there's a fundamental clock that introduces a preferred time slicing. Okay? And one of the ways of defining that time slicing is, for example, in terms of the expansion rate as a function of time. That also tells us how to define the slicing here. And then we look at fluctuations of that time slicing. So spatially varying fluctuations of that time slicing will introduce a preferred degree of freedom, which is the Goldstone boson of the spontaneously broken time symmetry. Okay? So this is something you can do independent of inflation. You can do this for any FRW cosmology. And this Goldstone boson will always parameterize the adiabatic sector of the fluctuations. If you have several fluids, there could be additional fluctuations that aren't of this type, but there will always be this adiabatic degree of freedom which corresponds to perturbing the time slicing of my spacetime. Okay? So since this degree of freedom is guaranteed to be there, and by Goldstone's theorem it's guaranteed to be massless, in fact, it's always going to be a degree of freedom in our low energy effective theory. Okay? We're always going to have this light field. We might have other ones to which this can couple, but the minimal case, just in terms of the symmetry breaking pattern, is going to be the fact that we have this Goldstone mode. Okay? So I want to take this as one of my fundamental fields. And then in addition, you could also, of course, have massless gravitons. Those will also be guaranteed to be there. So the minimal way of describing inflation, I think, is in terms of these two massless fields, this Goldstone mode of spontaneously broken time translations, and tensor fluctuations to the metric, which we could describe as gravitons. Okay? And since these are massless, these are also the degrees of freedom that will be amplified, whose quantum fluctuations will be amplified during inflation. You might have other degrees of freedom that are massive, but those massive fields are typically frozen and won't get large power during inflation. Okay? In a particular gauge, spatially flat gauge, you can think of this Goldstone boson also as directly related to curvature fluctuations. Okay? They're literally just proportional. So for the remainder of the talk, if you want, you can think of these two fields as equivalent. Okay? So we have curvature fluctuations on the spatial slices that we defined. Those are the Goldstone bosons, the scalar sector of the theory. And then in addition, we have tensor fluctuations to the metric as well. And as you know, of course, these curvature perturbations are what's sourcing temperature fluctuations in the CMB. And these metric fluctuations are what's sourcing the B-mode type polarization in the CMB. So precisely the 2 degrees of freedom that we have introduced on the basis of this symmetry breaking pattern are sufficient to describe, the main observables that we have in the CMB. Okay? So from this point of view, it doesn't seem necessary to introduce more than these two fields. Okay? And so then in this picture, slow roll corresponds to the limit where this Goldstone mode is nearly free. Okay? There will be no higher order interactions in this field. And they will have a relativistic dispersion relation. So slow roll corresponds precisely to the limit where this pi field, or the curvature perturbation, does not have a non-trivial sound speed, and it also doesn't have non-trivial interactions. There aren't any higher order interactions for this pi. So it's just a free field, as boring as it gets. And similarly, the tensor fluctuations also to lowest order in approximation, we can treat as a free field with relativistic dispersion. Okay? There are then two important scales that enter in these Lagrangians. So there's the scale that normalizes the Goldstone action, which I will call the symmetry breaking scale. That's the scale associated with the time evolution of the background. In fact, if you evaluate this scale here for a single field slow roll inflation, it's simply given by phi dot squared. So you can see that this is characterizing how fast the field is moving during inflation. Okay, so this is an energy scale that in some sense tells you how fast the clock is ticking that defines the expansion during inflation. And then the tensor sector, of course, is normalized by the Planck scale, which is the scale of quantum gravity. Okay? So two fundamental scales. This is just an artist's renditioning of these scales. So we have the highest scale in this picture is the Planck scale. The scale of time evolution is below the Planck scale, and then we have the freeze-out scale, which is the scale at which modes freeze when they cross the horizon during inflation. And so we would like to use observation to tell us what the ratio of these different scales are. Okay? So in particular, we know that the Hubble scale always has to be below the scale of symmetry breaking. Yeah? Because in fact, we want this Goldstone boson to be valid low energy degrees of freedom at this scale Hubble. And in fact, you can show that the power spectrum, the size of fluctuations and the curvature perturbations, is directly related to the ratio of the Hubble scale to this symmetry breaking scale. And this number here we know is 10 to the minus 5, so this ratio here is simply fixed by observations. So this hierarchy is 60. Okay? So we know this scale f pi, the time evolution of the background is 60 times as big as the Hubble scale. That's a fixed hierarchy. What isn't fixed by observations at the moment, at least, is the ratio between the Planck scale and the Hubble scale. Okay? That's determined by the size of tensor fluctuations. So if you were to observe tensor fluctuations kind of at the level suggested by Bicep, then the Planck scale is of order 10 to the 4 times the Hubble scale. Okay? And that's why it's so exciting to observe tensor fluctuations, because it would tell us this hierarchy between the two scales. Okay? And then we would know everything there is to know about this roll picture in terms of these fundamental scales. Okay? Now I just want to discuss, however, how to go beyond this picture, beyond those 3 fundamental scales. And so there are basically 2 things you can do. You can parameterize these deviations from slow roll by higher order self-interactions, going beyond just looking at free fields, or by changing the dispersion relation in the quadratic action. Okay? And in fact, we're going to do both in this first example. So when you introduce the sound speed, it turns out that you're both changing the dispersion relation in the quadratic part of the action, but also by symmetry, you're inducing cubic and quartic interactions that are tied to the value of the sound speed. Okay? So you can't just change the dispersion without at the same time inducing higher order interactions of a certain size. Okay? That's simply fixed by the spontaneous symmetry breaking pattern that we have in the time-dependent background. Okay? So this is going to be important. There's a symmetry that relates different orders in the perturbation expansion. So there are couplings in the quadratic action, and that same coupling appears in the cubic action and in the quartic action. So this is a very special case where we can actually use measurements of power spectra, which measure just the quadratic action, to learn something about interactions. Yeah? Usually, in order to learn about interactions, you have to probe those interactions directly, measure some kind of higher order correlations. This is a special case where actually a symmetry relates the two. And so in principle, we could learn about this particular type of interaction if we were able to measure something about the sound speed from the power spectrum. Okay, then this is just, okay, of course, you could reintroduce fake Lorentz invariant by rescaling spatial coordinates. If you do this, you simply rewrote the quadratic part of the action with new meter sticks, basically. Then this restores kind of some kind of fake Lorentz invariant, and then this looks more like an effective action which is suppressed by some scale. And so here I've simply rewritten the scale in terms of the symmetry breaking scale and the sound speed. Okay. And
so are you thinking of f pi as evolving by a renormalization group? Because it's related to epsilon, which goes from nearly 0, and it has to go to 1 to end inflation.
Yeah, so here I'm actually describing the fluctuations close to horizon crossing.
So it's sort of
so it's kind of,
but,
yeah.
And so the fact that there is a change in epsilon is not, but in terms of just the vision of this,
yes.
Can you map it into a renormalization group kind of flow of f pi?
I think so. In principle, yes. It won't affect anything I'm
know.
doing.
It's just,
but
it's
yeah.
just if you're developing a
Yeah.
language,
Yes.
it's a unique way to think about it.
Yeah. Yeah. Yeah, maybe I shouldn't think about this in real time, but it's something you can think about. Yeah. So at the moment, the way I'm presenting is I'm working at kind of lowest order in slow roll, where I'm treating this h dot as kind of constant, and implicitly this is assuming that I'm evaluating everything kind of in a small time interval when the mode crosses the horizon. But then you could adiabatically extend this and kind of do some kind of renormalization group. Okay, so what we see from this picture here, that there is, as we saw before, there's this kind of cutoff scale where something special happens. Yeah, this theory actually also breaks down at some finite momentum. Okay, this finite momentum is now related to the sound speed and to this symmetry breaking scale f pi. And notice that for small sound speed, this scale here is always suppressed, always smaller than the symmetry breaking scale. Yeah. While in the limit where I'm taking CS to 1, it goes to infinity. So this cutoff, the theory again reduces to the theory that's simply free. Okay, so that limit is also correct. But if in the limit where the sound speed is small, I have an extra suppression of the symmetry breaking scale. And you can define this a little bit more formally. You can ask about scattering of those pi particles at high energies. Those scatterings will violate unitarity. But up to factors of pi, this is just happening at the same scale lambda here. So then we have a new picture that in the limit where the sound speed is small, there's an additional scale that enters here, and it will enter in between the Hubble scale and the scale of time evolution. Okay? So the Goldstone bosons themselves, we're observing them here, but then we'd like to know, whether this theory of weakly coupled Goldstone boson makes sense if we extrapolate inside of the horizon to higher frequencies. And it does make sense, but at this scale here, it starts to become strongly coupled. Okay? And I can't just look at perturbative Fourier treatment of like we were doing it here. Okay?
Can I ask a stupid question? I'm trying to relate all this to what I know about Carl Lagrange.
Exactly.
In that case, lambda is like 4 pi bigger than f pi, and I'm confused why they flipped around.
Exactly, because here we had a sound speed that was, if this were relativistic, then you wouldn't have this splitting between f pi and lambda.
Okay, so
and it's precisely.
4 pi is what in the way you're talking about? You don't worry about the 4 pi as being, you're saying.
I do have a kind of a 4 pi here.
Right, but you're saying that. So
Yeah.
It's the sound speed.
Yeah, it's the sound speed that's splitting these here.
The other way to phrase it is in the Carl Lagrange interactions that are tied to the leading kinetic just because it's so non-linear. So you could think of this as like a higher derivative correction to the Carl Lagrange, where you have the freedom to control the coefficient. Where you don't, or what the term you're thinking of, you don't have the freedom to control this coefficient. Right. I see. But CS is like that number, and that changes.
But otherwise, this analogy with the Carl Lagrangians is a very good one, yeah. And so that's why I was calling it f pi and not something else. Yeah.
Can you show the formula that's related the scale lambda to epsilon versus speed of sound CA?
Here, yeah.
So what confuses me, that if you want a small speed of sound, it's merely the correction due to this d pi to the fourth term.
Yes.
Is comparable to the leading one.
Exactly. This is precisely the problem. Exactly. It breaks down in terms of the background field. So it's precisely the point I was trying to make. That's why I had to develop this new language. Okay. So otherwise, we could have just stuck with describing in terms of d phi to the fourth and truncate. This is precisely a framework that allows you to. We have a new expansion here. Yeah. This expansion remains perturbative, even the limit of small sound speed. Okay. But it's in terms of directly the fluctuations. Yeah. And the background itself, in fact, will be strongly coupled. There will be no expansion with d phi to the fourth. But that's precisely the point. We'd like to decide whether the background is in this regime where it truncates or not. Yeah.
It doesn't think about that. The other thing is that this framework doesn't. At this point, one hasn't even assumed that there was a scale, right? So you don't even thinking of this as an expansion. You could again, if you like the Carl Lagrange, you could say he's trying to decide whether the Carl Lagrange came from an actual fundamental scale or it came from something else in time.
Even the Carl Lagrange, before the negative terms become as important as the derivative terms, you don't believe that.
But at that energy.
Yeah.
But below at sufficiently low
Lower,
energy,
yeah.
it makes sense that we're working at those.
Yeah. There will be. Yeah. Okay, so then in this picture we have this these type of scales, and as we saw, because the sound speed is tied to this higher order interaction in terms of observables, this hierarchy h2 over lambda, unsurprisingly maybe, can be related to the amount of non-Gaussianity and the fluctuations. So we have this non-Gaussianity parameter FNL. In fact, the true size of non-Gaussianity is kind of FNL times the size of curvature fluctuations, the 10 to the minus 5. That combination can be written as the ratio of h over lambda. Or, if I were to plug in my previous definition, you will find that FNL is of order 1 over CS squared. Okay? There's an enhancement of FNL for small values of CS. Okay? So let me go back here, in fact. So we would like to decide whether this scale, this unitarity bound or strong coupling scale, however you want to call it, whether that scale happens above the symmetry breaking scale. And I can therefore describe my theory as weakly coupled Goldstone boson in the entire regime of energies where it applies. Okay? Here we know something else happens and we have to include the background field anyway. So we want to decide, is it weakly coupled at all energies up to here? Or does it become strongly coupled before that happens? Okay? And that transition between You know, in the special case, the transition happens precisely when these two scales here coincide. Okay? So you can calculate a special sound speed corresponding simply to the coincident limit where this unitarity bound is of order the symmetry breaking scale. Okay? And so what you find is that this is of order 1/2. Yeah? So there's very small sound speeds corresponding to non-perturbative physics. 1/2 is the critical value, and then there's a window of perturbative description where the sound speed is between 1/2 and 1. Okay? And you know, if you want to again relate this to observables, you will find that this corresponds to an FNL value of order 1. Okay? And so for that reason, we think that an order 1 equilateral non-Gaussianity is kind of a threshold value and an observational target to be able to decide, you know, with confidence, you know, where in this picture you actually live. Okay. So then let me quickly tell you about observational limits on these parameters. So as we already saw, for small sound speed, you enhance scalar self-interactions. You produce this non-Gaussianity. Planck has, however, not found any of this non-Gaussianity, so he puts an upper limit on this value FNL. And that upper limit we can translate into a lower limit on the sound speed. And so what that limit here translates into is we know that the sound speed has to be bigger than about 2%, 0.002. Okay? But you might think that this is a surprisingly weak bound on the sound speed. Yeah? It's still relatively far. There's a really large window of non-slow roll behavior between 0.02 and 1/2. Okay? So I'd like to use this value of 1/2 to really be able, as soon as the sound speed is greater than 1/2, I'd like to call it slow roll. If the sound speed is less than 1/2, then that's genuine non-perturbative, non-slow roll behavior. Okay? But current observations of non-Gaussianity, you know, still leave this window of about an order of magnitude, where you could have non-perturbative physics that is significantly away from slow roll.
So why are you using this terminology? Because you said you dispose of the scalar field, so there's no scalar which is slowly rolling, and you still slow current slow roll, just because when you go to 1.
Sorry?
Why are you using this terminology?
This is, well, on the previous slide I was calling it non-perturbative and perturbative. Here we're just trying to connect to the original question of being able to decide whether we can confirm slow roll or rule it out. Yeah, and so, yeah, if you don't want to think about fundamental scalars and slow roll, the most general way of talking about this is in terms of just perturbative or non-perturbative.
But this has nothing to do with the epsilon and delta parameters, does it?
Sorry?
Does it have to do anything with the epsilon and delta parameters or slow parameters?
No.
It does not.
No.
It's
No.
confusing in this sense.
No, because this is about the kinetic dynamics. Yeah, epsilon just tells you about h dot. Yeah. So epsilon will always be small for any inflationary mode, by definition. That's how we define what inflation is h dot much less than h squared. Okay. So that's I think the nice thing about this framework is all it's assuming is that there is a phase with h dot less than h squared. Okay. And it's not assuming where this. It's a separate question where this came from, and you just study fluctuations around this background. Okay. And you can match, okay, if you're tied to one particular type of producing h of t, you can try to match those things together, but this is a more general, I think, description.
But buried into this, with the time slicing, if you go to uniform scalar field slicing, which is, I think, how some of this is motivated,
yes,
there is the potential energy density at that time. And somehow, in what I'm looking at, what you're writing, it's buried somewhere that I can't really see. But you know, the usual way of thinking about things is, you know, you're rolling down potentials, and they have steepness, which gets you out of, which gets you into a situation where the momentum is comparable.
Yes.
How did that actually manifest? Is it because of that time?
I think it manifests itself in the fact that this action for the fluctuation didn't have a linear term. Yeah. So if you were to just write down this action for the fluctuations with arbitrary coefficients, yeah, you said you didn't even know you live in FRW. Yeah, it's just arbitrary functions of time. Then the zeroth order action and the first order action, the coefficients there will be fixed by the Friedmann equations. Yeah, and so that's somehow where your intuition of the background dynamics, it comes from the absence, the fact that I don't have tadpoles, don't have, you know, linear instabilities in this action, was fixing implicitly, kind of relating the cosmological constant to evolution of h h of t and so on.
I think this is either a paraphrase or it's completely off the mark, but there's the Mukhanov-Sasaki variables.
Yes.
And I think that if you take your equations and then that's the equation you get out.
Yes.
And in that equation, the potential is manifested in epsilon. And your epsilon is somehow manifested in f pi, but f pi, as I said before, it's actually changing because the potential is changing.
Yes.
And so what must be very important here is that f pi is a sliding scale as opposed to it being a fixed scale. So you're in the epsilon approximately 0 limit, and it must be important.
No, but if you don't keep epsilon constant, then you could get corrections to this of order, eta and epsilon squared and so on.
Since ns, are great observable, is maybe it's proportional to epsilon, but it's also got that epsilon
I agree.
Which is probably a dominant meter.
True. They're in here. I can show you. But so since we're focusing on the large self-interaction sector,
okay.
and
that's good. But if you're keen about ns, you have to add a dot.
Very true. Very true. Very true.
Good.
Yeah. Of course, this would just give you perfect scale invariance and so. Yeah. But just to show you, actually, this, if you want, you can call the Mukhanov-Sasaki variable.
Yeah,
this pi c
that's what I thought it was.
Yeah.
Sorry. Feel free to shut me down, but you motivated this thing by starting with this orderly term, okay? But clearly, whenever this gives you a speed of sound,
I agree. Please. Fine. Yes, dBi. So there's
that's what I thought. Okay.
So there is a resummed version where you can write this as square root 1 minus phi squared. Okay. But it's but again, the way I was introducing this is because some people connect it closer to home. Okay. So if you are close to the chiral Lagrangian, then please, by all means, start from there. Yeah. So. Okay, so we have found that just looking at self-interaction, the couplings at higher order, that doesn't bound the sound speed yet by a very big amount. And so there's still this window, and we'd like to know, can you learn more about this part of the space? And so there's a second effect that, in fact, arises when you have a small sound speed, which is that you're also enhancing the scalar power. So you can derive this power spectrum of scalar fluctuations. In slow roll, this would just be a ratio of h to the fourth and then m Planck squared h dot. In the case where you have a non-trivial sound speed, this gets an extra boost, just because you're enhancing spatial gradients for a small sound speed. And then in addition to that, also you have tensor fluctuations which are independent of the sound speed, and so they don't feel this change in the dispersion. Okay. So when you calculate the tensor to scalar ratio, you get the familiar part, which is 16 times the slow roll parameter. And you get a correction which is given by an extra suppression coming from the sound speed. All right? So measuring the tensor to scalar ratio tells you about a combination of two types of symmetry breaking. It breaks the time translation symmetry of the spacetime. That's given by epsilon. So that's the CITA breaking. Okay? And then there's the non-trivial sound speed, which is the Lorentz breaking. Unfortunately, these guys look almost the same. So it's hard to. But, okay, but this formula then implies that if you were to observe tensor at a certain amplitude, anything bigger than say 1%, it would also imply a lower bound on the sound speed because I can simply rearrange this formula. I can write it in terms of CS. If I have a lower limit on R, that will give me a lower limit on CS. Okay. So before you complain that this is a kind of a useless bound because it's dependent on an unknown parameter epsilon. Okay. So in principle, you could say that this bound would weaken if I were allowed to have larger values of epsilon. Okay? So to really establish a bound, you would have to establish that something happens when you make epsilon large that violates some of your other observations. And so in fact, as soon as epsilon becomes bigger than say 10%, which still is slow, which still is inflation, but larger than we usually think of it, there are in fact two new effects that kick in. So first of all, the scale invariance of the scalar fluctuations is in danger. So precisely for the reason that Dick was saying, that if an evolving slow roll background doesn't produce precise scale invariant fluctuations, if I make epsilon too large, actually the scale invariance will be spoiled by too large of an amount. So that's something you have to worry about, but in principle you could cancel that off by canceling it against the second derivative of evolution and so on. So this is not an absolute thing. It's an aesthetic worry that you might have, but in principle you could fine-tune your way back to a scale invariant spectrum. But a second interesting thing that I wasn't aware of when we looked at this, I mean, I knew of the fact, I didn't know it was important, is that tensors and scalars freeze at different times. Okay, so when you have a sound speed, the real scale of freeze out for the scalar fluctuations is actually the sound horizon rather than the physical Hubble scale. And so scalar fluctuations, in fact, freeze out slightly earlier than the tensor fluctuations do. Okay? So this means that there's actually an extra correction to this formula that I just showed you, the 16 epsilon CS, which is given by this difference in the ratios of the two Hubble scales at the time when the tensors freeze out and at the time when the scalar freeze out. And what's important is that this ratio is always a suppression. Yeah? Since the Hubble scale is decreasing during inflation, that's dictated by the null energy condition, h at the time of freeze out of the tensors is always going to be smaller than h at the time of the freeze out of the scalars. So this ratio will always be less than 1, and so actually this will always have the tendency of suppressing tensor fluctuations. Okay? And so you can already qualitatively see that if I have an additional suppression for the tensor fluctuation that also scales with the difference of the sound speed to the speed of light, I will make it even harder on myself to allow to go to small values of CS. Okay?
How much of this goes over into isokurvature modes?
You mean the difference in the freeze out and
Sound speed is explicitly for the inflaton, effective inflaton degree of freedom, but an isokurvature mode
can have a sound speed also.
It would be, well, it could have sound speed, but it can also just have c equals 1.
Yes.
And it would be, behaving somewhat like tensors in terms of freeze out.
Yes, yes.
So I don't know, is that an interesting effect?
I think it is. I was discussing this effect with Liam at some point because there's a question of, this is also related to the Lyth bound, for example, which also relates, one way of imagining to evade the Lyth bound would be to mess up your scalar. Rather than, the tensors seem pretty pristine. You can't change much about the tensor fluctuations. But as we already saw, even for the sound speed, this power spectrum you can change. You can also change it by having additional sources, isocurvature fluctuations. So you might wonder whether in that way, by changing the scalar fluctuations, you can avoid this conclusion that you have to have super Planckian transversal. In that case, we decided that actually you couldn't. Isocurvature fluctuations was always making it worse. But we can look at that. There are things to think about, but okay. So in fact, you will see this. Even in perturbation theory, you would see this effect if you go to a higher order in slow roll. At second order, you in fact have a correction to this formula that is known. So this is of order epsilon squared, but interestingly, this isn't just epsilon squared, but it's also multiplied by log CS. Yeah. So there's a large log in this perturbative expansion that if I'm making the CS, I can't make the CS arbitrarily small without, breaking this expansion. Okay. And in particular, this is large in the regime of interest. So the regime of interest, imagine you take the Planck bound for CS, which was kind of 10 to the minus 2. You take an epsilon, which you want to drive towards 0.1. Then actually this combination here isn't smaller than 1. Okay? So precisely in the regime of interest, in fact, this expansion here would break down. However, instead of doing perturbative expansion, you can imagine solving the evolution directly, exactly. And so what you would find let's first do the simple case where epsilon is constant. So if epsilon is constant, you can solve this evolution exactly. You get the strange formula for R, okay, which is 16 epsilon, then CS, and raised to this power. If I were to expand this power at first order in epsilon, I would get back this logarithmic correction, but now this is valid for larger values of epsilon and smaller values of CS. Okay. Then if you look at this formula or you go to and plot it, you'll find something like this. So here I'm showing you R as a function of epsilon for different values of CS. So imagine we're picking a constant value of CS, which is indicated here by this dashed line. And then as I'm going to larger values of epsilon, naively you expect for larger values of epsilon, the 16 epsilon CS increases and you get larger tensors. But actually there's a maximum in this Yeah? And if I make epsilon too large, then this splitting in the free result between the tensors and the scalars as two, actually leads to a suppression that overwhelms the increase that I naively expect, and you get this turnaround. So actually, there's a maximum for fixed value of CS. There's a maximum value of R that's dictated by this new effect. And then, of course, you could turn this around and get, this then implies that there's, for a given value of R, there's a lower bound on CS. You can't make CS too small without violating this maximum value of R. Okay? So just for reference here, I'm showing you m squared phi squared has an R value of kind of 0.1. This is given here by this dashed line. And so that would correspond to a bound on the CS value, which is bigger than 0.1, something like that. Of course, it's dependent on R, whatever R would be observed. For smaller values of R, you would get weaker bounds on CS. And for larger values of R, you get stronger bounds on CS. And maybe in the interest of time, let me kind of skip this. You can extend this resummation of this large log to higher orders in slow roll. Particularly, you can relax this assumption that epsilon was constant, which is kind of a strong assumption. You can allow the sound speed to vary with time as well. You get kind of more complicated formula, but kind of qualitatively similar behavior. Yeah, maybe let me skip this also. It turns out when you include these higher order corrections carefully, you slightly strengthen the bound. And if you also fold in the fact that you want to remain scale invariant fluctuations with small running and so on. So whoever wants to see those details, I'm happy to explain, but I shouldn't take too much of your time. Okay. You might worry that because this is now, if you include higher order slow roll parameters, this is a higher dimensional parameter space. So you might worry that we might be missing some degeneracy directions where you have no bound. Analytically, we weren't seeing any of those. So we couldn't resist the temptation of trying, to actually look at data and see if there is such, numerically to see if there is such a path in fields in parameter space that has no bound on CS, and we didn't find it. So these are just different combinations, different marginalizations, and we get of the order. We always get kind of results that are consistent with our analytic argument. Okay, so let me just conclude this part. So I think what we conclude is that if we were to observe tensors at any value that's bigger than about 1% in R, that would lead to a bound on CS or FNL equilateral from this particular interaction that's stronger than the Planck-only bound from non-Gaussianity. And if R is really as large as suggested by something like m squared phi squared, then actually this bound on CS is stronger by an order of magnitude, which means on FNL it's actually stronger by almost 2 orders of magnitude, because FNL scales as a square of CS. So increasing the bounds on CS actually allows you a handle on particular types of interactions, and FNL value is much stronger than what you would get if you try to measure those interactions directly. Okay. Any questions about this part? Okay. So I'll spend 5 minutes. How much do I have then? 5 minutes?
5 minutes.
Yeah. Okay. I'll spend 5 minutes on part 2. Part 2 is not, no worries. It's not as long. They weren't equal parts. But I'll skip a few slides and I'll just give you the punchline of this part. So just to remind you, so we had first looked at this case where the spectrum of states was a single light field, and then the only degrees of freedom in addition to that light field were above some very high scale, and we were integrating out those fields. That leads to interactions by coupling this field to that field, but those interactions are suppressed by this energy scale. That was the case that kind of we were having in mind earlier. Now I want to look at the situation where there might be additional fields below this scale, so they play part in the, they are, like Dick was mentioning, additional fluctuations during inflation. And either those have masses which are of order the inflaton field, so it's even a bit ambiguous whether you call them, you should, which of those fields you call inflaton and which one you give some other name. Or they can have masses, that are clustered around the Hubble scale. That's also, for particle physicists, that's a scenario that is kind of attractive as well, because if a field isn't protected by any symmetry, then during inflation it will receive corrections from the positive vacuum energy, but those corrections are limited, and they're limited by the Hubble scale during inflation. So it's a very natural scale to expect masses to have if they're light before supersymmetry breaking, but receive masses from the breaking itself. For what I'm going to say now, it's not going to be so important which of these two cases we're in, but if people are interested in this particular example, I can describe this. Okay, so then we have two sectors. As before, we have the inflaton sector. Here we're going to start off with just the slow roll action. A flat potential, meaning that we have scale invariance because of an approximate shift symmetry of the inflaton field. Now we're going to add to this a second sector. I'm going to call this a hidden sector. That sector can now have much larger interactions than the inflaton because it's not the fluctuations that we observe directly in the CMB. We only see them after conversion. And in particular, it's not what's driving the background expansion. So it doesn't have to be, these interactions don't have to be small in order to preserve slow roll. Okay? So we can have a mass term for those fields. We can also have cubic interactions and so on. And so what Dan and I also showed is that this cubic interaction, for example, can also naturally be large afforded the Hubble scale without destabilizing this sector and inducing large masses. If you take this action, calculate some loop, having a large coupling here, as long as it's smaller than Hubble, won't induce a mass here which is bigger than Hubble. Okay? So it's stable in that sense. Then we're imagining in effective theory, you should write down all possible couplings consistent with the symmetry that we have postulated. So far, we have a shift symmetry for phi, but no shift symmetry for sigma. So the lowest dimension operator that you can write down consistent with those symmetries is this one. I showed it earlier. And so what we want to do is we want to use data to put a constraint on this scale lambda. Okay? Here then, this is just standard. We're going to, as before, we're expanding in background and fluctuations. Now everything is actually weakly coupled at the scale that we care about, so we can work in terms of perturbations around some classical background trajectory like this. And so as you can see here I've just drawn diagrams that shows you the different types of interactions. There's a massless field, which is the inflaton fluctuations, a massive field, which is this extra sector. They couple linearly to each other because there's this kinetic mixing term that I showed you. There's also a cubic interaction that also comes from the kinetic mixing. There's a mass and a cubic coupling that comes from this part of the Lagrangian. And then you can solve this system numerically. In some regions of parameter space, you can solve it analytically. But if you want to know it for all values of lambda, you solve it numerically. And there it's good if you have an excellent grad student, which is my student Valentin Assassi, who did basically everything here. So what he found when he was simulating this and was calculating the three-point function that's induced by this Lagrangian, he found these particular exclusion contours. So what I'm showing here is the strength of the mixing interaction. So these fields are weakly mixed if lambda is big, and you're suppressing this higher dimension operator. And they're strongly mixed for smaller values of lambda. And then this extra sector is very non-Gaussian or strongly coupled if this A here is big, and it's very weakly coupled in Gaussian if A is small. Okay? So there are two important limits that you can understand analytically. There's a universal bound that comes from the fact that this kinetic mixing interactions that we had itself has interactions. So as soon as you mix, you also produce non-Gaussianity at a minimal level here. Okay? So lambda has to be bigger than about more than 100 times the Hubble scale in order to be able to write down this perturbative theory. But if you introduce a self-coupling in the hidden sector as well, you get an additional bond which is much stronger in principle for large values of this self-coupling. Okay? And in this limit, this is the limit that for the rest I just want to say a few words about. In this limit, you can calculate FNL. Okay? It has a very large prefactor, which is given by the inverse of the power spectrum squared. So this FNL starts its life at 10 to the 10. Okay? But then there are several factors. Suppressing this prefactor, given by the weakness of the coupling in the hidden sector and by the suppression of lambda over h. But in order to get to any observationally allowed values of FNL, smaller than 10 or 100, you can already see that this scale lambda has to be rather large, as we can see here as well. Okay? So you have to live above this line here. So you have to have this interaction is only allowed to be present if it's suppressed by a scale that is 10 to the 5 times bigger than the Hubble scale. Okay, so that's rather unusual because usually we think when we observe in the CMB, we learn something about physics at the Hubble scale. That's when the mode is freezing out. But here, indirectly, by also making a very precise measurement of the amount of Gaussianity of the fluctuations, we're actually learning something about energy scales much higher than the Hubble scale. Okay. So this is what I think this shows. If you turn around bounds from Planck on FNL, you'll get lower bounds on lambda of order 10 to the 5 times the Hubble scale. So you learn something about physics at much higher scales than you naively would have thought, just because you make very precise measurements of something. Okay. And then there's another nice coincidence that if you turn this around, 10 to the 5 times Hubble might ring a bell to you. This was also precisely the splitting between the Hubble scale and the Planck scale for large tensors. So if you were to rewrite this expression in terms of the tensor to scalar ratio, okay, any value of R that's bigger than 1%, okay, would imply, for generic values of these self-couplings, would imply that you're constraining interactions, of order the Planck scale. Okay. So a big if, of course, if gravity waves are observed, then this would kind of put a strong constraint on interactions suppressed by the Planck scale. Okay, so then let me stop here. So I think what we have seen here is that we have quantified two of the most well-motivated, I think, deformations away from slow roll, and to kind of see how far we are, anyway. And so far, I think it's still slow roll is favored by data. Yeah. Thank you very much.